Hey everyone, and welcome to another deep dive. Today we're talking about something that's both familiar and mysterious. Rain. You know, the wet stuff that falls from the sky. We're diving into the science behind it thanks to a fascinating transcript you sent over from the Quantum Fracture YouTube channel.
Ah, great choice. They always have a knack for making complex topics both fun and understandable.
Right, and they jump right in with this question. I don't get rain. And it's true, we see it all the time, but how often do we really stop and think about what's going on up there?
It's easy to take for granted, isn't it? Like, we know it rains, but the how and why, that's where things get really interesting.
Totally. Like, here's a simple one to start us off.
Right?
Why are clouds white? I mean, we all know water is clear, right? So what's the deal?
Yeah, that's a great question. It has to do with how light interacts with the water droplets in a cloud. Think of it this way. A glass of water looks clear because light passes through it pretty easily. But a cloud, it's packed with millions of tiny water droplets, all suspended in the air. And those droplets, they scatter sunlight in every direction. So instead of light passing straight through, like with a glass of water, it's bouncing around all over the place.
Exactly. It's like a disco ball up there, scattering light everywhere. And because the droplets are all jumbled up in different sizes, they scatter all colors of light equally. And when all colors of light mix, what do we get? White light.
Ah, that makes sense. So it's like how a snowflake looks white, even though it's made of clear ice crystals. Each tiny crystal scatters light, and together they create that bright white appearance.
You got it. It's the same principle with clouds. Those water droplets are like tiny prisms, scattering light and creating that brilliant white we see.
Wow, that's amazing. I never would thought of it that way. It's incredible how even something as simple as a white cloud has this whole hidden world of science behind it.
And that's just the beginning. There's so much more to uncover about rain, from how those tiny droplets form in the first place to the incredible power of thunderstorms.
Speaking of which, one thing I always found fascinating is how raindrops actually stick together. Like you'd think they just fall apart, right?
Well, there's a force at play here that's stronger than it looks. Surface tension. Water molecules are naturally attracted to each other, kind of like they're holding hands. This attraction creates a sort of skin at the surface of the water droplet.
Oh, I've seen that. Like when you put a drop of water on a table and it beads up instead of spreading out completely flat.
Exactly. That's surface tension in action, and it's surprisingly strong for something we can't even see. In fact, it's what allows those tiny raindrops to hold their shape and cling to your window after a storm.
So it's like the water molecules are forming this microscopic net that keeps the raindrop from falling apart. That's so cool. But then, if those droplets are so small, why don't they just float around in the air forever? What makes them heavy enough to fall as rain?
Another excellent question. And that's where the journey of a raindrop gets even more interesting. You see, those tiny droplets we see in clouds, they need to grow much, much larger before they can overcome the air's resistance and fall to the ground as rain.
How much larger are we talking here?
We're talking 1,000,000 times their original size. 1,000,000 times larger. It's quite a growth spurt for something so small.
A million times, that's mind-boggling. So how do they do it? What's the secret to a raindrop's incredible growth?
Well, there are a couple of different processes at play here, and it all depends on the temperature inside the cloud. It all depends on whether we're talking about a warm cloud or a cold cloud. In a cold cloud, which is what you might find at higher altitudes, the process involves ice crystals. They're kind of like the seeds that help raindrops grow.
Ice crystals. But I thought rain was, well, rain, not ice.
You're right, rain is liquid.
Yeah.
But up high in a cloud, where it's much colder than down here at ground level, water can exist in a supercooled state. It's still liquid, but way below its freezing point.
Super cooled water. So it's like it's holding its breath, waiting for something to nudge it into becoming ice.
Exactly. And those ice crystals provide that nudge. You see, ice crystals have this amazing ability to attract those supercooled water droplets. When the droplets hit the ice crystals, they freeze on contact.
Ah, so the ice crystals are like little magnets pulling in those super cool droplets and making themselves bigger.
Precisely. And as those ice crystals grow larger and heavier, they start bumping into each other. Some of those bumps are just glancing blows, but sometimes they collide head-on, and those collisions can knock off even more tiny ice particles. It creates this chain reaction of collisions and growth.
So it's like a snowball effect, but with ice instead of snow.
Perfect analogy.
Sure.
And eventually, those ice crystals become so heavy that they can't stay suspended in the cloud anymore. Gravity takes over, and they start to fall. Now, if the air near the ground is warm enough, those ice crystals melt on their way down and reach us as raindrops.
Okay, that makes sense for cold clouds, but what about those warmer, more humid days when the clouds seem closer and it's definitely not freezing up there? How do raindrops form when it's warmer?
That's where the warm cloud process takes over. It doesn't rely on ice crystals at all. Instead, it's all about collisions. Remember those tiny water droplets we were talking about? Well, inside a warm cloud, they're constantly moving around, jostled by air currents and bumping into each other.
So it's like a microscopic mosh pit up there with water droplets bouncing around instead of people.
Exactly. And just like in a mosh pit, some of those collisions are more intense than others. When two water droplets collide with enough force, they merge together, forming a slightly larger droplet.
So it's like they're fusing together on impact, but wouldn't they just break apart again as easily as they came together?
That's where surface tension comes back into play. Remember that skin we talked about?
Mhm.
It helps hold those newly merged droplets together.
Oh, so it's like surface tension is acting as the glue that keeps those bigger droplets from falling apart.
You got it. Now, this process of collision and merging repeats itself over and over again, with larger droplets falling faster and sweeping up smaller droplets in their path. Eventually, you get droplets that are big enough to fall as rain.
Okay, so that's how raindrops form in both cold and warm clouds. But there's one thing I still don't quite get. You said those tiny cloud droplets need to grow a million times larger to fall as rain, right?
That's right, they need to grow from just a few micrometers across to a few millimeters, which is a huge difference in size.
Exactly. So how do they bridge that gap? I mean, we've talked about how they grow through condensation and collisions, but is there something else going on?
That's the million-dollar question, and it's something that has puzzled scientists for a long time. You see, we understand how those very first tiny droplets form and how the larger ones grow through collisions. But there's this middle ground, this awkward teenage phase of raindrop development, where the droplets are too big to grow efficiently through condensation alone, but not quite big enough for collisions to be super effective.
So it's like there's this missing link in our understanding of raindrop growth, this mystery zone where we're not quite sure what's happening.
Precisely. There are theories, of course. Some scientists believe that turbulence within the cloud might play a role, concentrating those mid-sized droplets and making collisions more likely. Others are investigating whether electrical charges within the cloud could influence how droplets interact and grow.
Wow, so there's still so much we don't know. It's amazing to think that something as familiar as rain can still hold such mysteries.
It just goes to show that the world is full of wonders, even in the most everyday things.
Absolutely. But speaking of wonders, we can't forget about one of the most electrifying aspects of rain, lightning. The quantum fracture video mentioned that 50 lightning bolts strike Earth every single second. That's mind-blowing.
It's a powerful reminder of the forces at play during a thunderstorm. And lightning is actually closely tied to the process of rain formation, especially in those big, powerful storm clouds.
Oh, right. Because lightning is all about electricity. And we were just talking about how electrical charges might play a role in raindrop growth. So how does it all work? How does a cloud go from holding water to shooting bolts of lightning across the sky?
Well, you have to remember, those storm clouds are like giant atmospheric generators. It all starts with those collisions between ice crystals and graupel we were talking about earlier.
Right, those little hailstones bumping into each other. But how does that create electricity?
It's kind of wild, actually. When those ice particles collide, especially in the turbulent updrafts and downdrafts of a thunderstorm, they transfer electrical charge between them. It's like they're swapping electrons in midair.
So just by bumping into each other, they create this electric charge.
Exactly. And here's the thing, the graupel, those little hailstones, they tend to become negatively charged. The ice crystals, they end up with a positive charge.
So it's like the cloud is becoming this giant battery with positive and negative charges building up.
You got it. The lighter, positively charged ice crystals get swept up to the top of the cloud by those strong updrafts. Meanwhile, the heavier, negatively charged graupel sinks to the bottom.
Okay, so we have this massive separation of charges, like a giant invisible force field inside the cloud. But how does that actually turn into lightning?
Well, think about it like this. The air around us acts like an insulator. It's usually pretty good at preventing electrical current from flowing freely.
But obviously lightning does happen, so something must be overcoming that insulation, right?
Exactly. When the difference in electrical potential between those positive and negative charges, either within the cloud or between the cloud and the ground, becomes great enough, it's like the air just can't hold it back anymore.
It's like trying to stop a waterfall with a sheet of paper.
More like trying to stop a lightning bolt with a sheet of paper.
Yeah.
But you're getting the idea. When that electrical pressure, that potential difference, gets too strong, it overwhelms the air's insulating ability, and boom, you get a discharge of electricity.
Lightning. It all happens so fast, but what's actually going on in that split second?
It's pretty incredible when you break it down. First, the negatively charged part of the cloud sends out a kind of feeler called a stepped leader. You can't see it with the naked eye, but it's basically a channel of charged air that zigs and zags downward, searching for a path of least resistance to connect with the positively charged ground below.
So it's like the cloud is reaching down, trying to find the easiest route for that electrical discharge.
Precisely. And as that stepped leader gets closer to the ground, you often see positively charged streamers rising up to meet it, usually from tall objects like trees or buildings.
So it's not just the cloud reaching down, but also the ground reaching up.
Exactly. It's this incredible electrical dance. And when those two paths, the stepped leader and the streamer, finally connect, it's showtime.
Lightning strikes. But we're not done yet, are we? Because there's also thunder, and it's always a little delayed after the flash of lightning.
Right. And that delay is actually the key to understanding what causes thunder. You see, that electrical discharge, that lightning bolt, generates an insane amount of heat, like 5 times hotter than the surface of the sun.
Wow, that's unbelievable. And that heat is what causes the thunder.
Exactly. This sudden, intense heating causes the air around the lightning bolt to expand incredibly rapidly. It's like a mini explosion, and that creates a shock wave.
And that shock wave is what we hear as thunder. It's amazing how something we experience as a single event, lightning and thunder, is actually this complex chain reaction happening at an incredible speed.
It's a powerful reminder of how much is going on around us that we don't even realize. And speaking of things we don't always see, did you know that lightning can actually create antimatter?
Antimatter, like the stuff they talk about in Star Trek.
The very same. It's a recent discovery that really blew our minds. Those incredibly energetic gamma rays that lightning produces can interact with air molecules in a way that creates pairs of electrons and their antimatter counterparts, positrons.
So, for a brief moment, you have both matter and antimatter existing side by side, created by a bolt of lightning. What happens then? Do they just cancel each other out?
Exactly. Matter and antimatter can't coexist for long. They annihilate each other in a burst of energy. It's like a microscopic Big Bang happening right above our heads.
This is incredible. I never would have imagined that something as seemingly simple as rain could involve so much mind-blowing science.
It just goes to show you there's always more to learn, even about the most familiar things in our world.
And that's what makes exploring these topics so fascinating. It's like peeling back the layers of reality and discovering a whole new world of wonder underneath. So, to our amazing listener who sent in this rain-soaked topic idea, we hope you've enjoyed this deep dive. And to everyone listening, keep those questions coming because you never know what amazing secrets we might uncover together. Until next time, stay curious.